Hey guys, so this video is going to help you with the fifth lab where you launched at different angles and you recorded the ranges at those angles. This is only for the part 2 lab where you're launching at several different angles, not the horizontal projectile, but just the general projectile. So you can see that in the title up here. So I have my data table set up, experimental data. So this is what I recorded in class, and we're going to develop this now through this video. Okay. This actually should be 90 degrees. So I put 2 extra data points here that we didn't actually measure, but it's because I told you guys it was dangerous. But we can kind of see that if you launch it at 0 degrees, it's not actually going to travel. We're only putting this and 90 degrees on a data table so that our graph looks nicer and more complete. You'll see what I mean when I actually create the graph. So you can include these as your data points as well. 0 degrees at 90-degree launch would give you 0 range, right? If you launch at 0 degrees, you don't actually leave the ground, so you don't have a range. And if you launch it straight up, you can assume that it's not going to move anywhere either, right? Now, experimental range, what I put here, I put experimental range because it's going to help with the labeling on the graph, but really this is the average, right? So we've done this before where to find the average of your 3 trials, you do equals average, open parentheses, and highlight all the values you want to average, close parentheses, enter, right? So that's average of 0, which is 0, and you can drag this down to repeat the same calculations for all the rest of them, right? So that's our experimental average ranges. And you're going to be graphing this on a graph, which we'll do in a second because I want to graph this one also. Now, theoretical data is based on the equation that we talked about in class. I told you that you had to research why this equation is true, and there's tons of equations online, and I'll link some of them in the YouTube video underneath in the description. But we're given this range equation, right, that you have to explain in your lab report. Specifically at 45 degrees, theta is 45, so then it becomes vi squared sine 2 times 45 degrees over g. The reason why this is nice is because you get sine of 90. Sine of 90 we know is 1, so vi squared times 1 over g gives you just vi squared over g, right? And if you use this to solve for vi, you get this equation. Vi is equal to the square root of range times g. Now we're using our data from our 45-degree launch to find out what Vi is for a theoretical value. So back here, I put a section here where I'm going to calculate what the Vi is. Now we see here it says square root of range times G. So I'll literally do that. And range specifically at 45 degrees, right? So equals square root, which is SQRT, parentheses, our range at 45 degrees, which I got to be this value, times g, which is 9.81 on the surface of Earth, close parentheses. So I got that my initial velocity based on my data is 3.06 meter per second. Okay. So we want to find the theoretical ranges at all these values, right? So we go back to this equation, and we're basically plugging in this stuff with the values we know. We know that our Vi is this, so it's equals to Vi squared. I want to put this in parentheses just so it can separate things to make sure I don't make any mistakes. Vi squared, which is this guy squared, times sine of 2 theta. Sine of 2 times, now we talked about in last time that Google Sheets does all angles by radians, right? We have it here in degrees. So to convert that, we do radians, parentheses, and then the angle. So it's sine of 2 times this angle in radians. Close parentheses, close parentheses, close parentheses. The nice thing is if you watch carefully, it shows which pair of parentheses are highlighted, and that tells you that this close parentheses closes this guy, right? So we're all closed up. So sine of 2 theta divided by g. So we can divide all this by 9.81 because this is happening on the surface of Earth. Enter. 0. That's what we expect. When you launch at 0 degrees, you should get a range of 0. Now, we also talked about this one little neat trick, is that when you're referencing this stuff and you drag all the way down, it assumes that every single cell that you referenced here, specifically in this case H2 and G2, it wants to refer one down when I drag this. But you notice here, this VI term, we don't want to have this next equation reference the cell below it, because that's not even a number. So to keep it referencing this one specific cell, you put a $sign in between the letter and the number. $2. Enter. So now when you drag it down, you notice that our next value still references H2, but now it's G5. This next one still references H2, but now it's G6, right? Which is exactly what we want. We want to use the next angles while keeping the same VI cell. So this is our theoretical value, and just eyeballing it, it looks pretty good. To be honest, I made up these numbers so that they are going to be really good. If yours aren't like this, don't be afraid, right? You just need to be able to explain why your values are not exactly what you expect. And there's tons of error in this, which we've talked about in class. So now you need to make your actual graph. So you go Insert, Chart. Now this is probably the only lab in the entire year where it actually looks nicer if you don't use a scatter plot. Instead, we're going to use a smooth line chart. Okay, that way you get to see how it actually curves. We didn't take enough data points for it to look like a really nice curve. So a smooth line chart actually looks a little bit better in this case. So we're going to actually use this one for this lab. Okay. Our x-axis, we're plotting range versus angle of launch. So our angle of launch in degrees is all of our x values. And notice I'm highlighting the title of it also. Okay. And our series, same as before, series is our y values. We want to graph the experimental range. And we also want to graph, I'm adding a series again, our theoretical range values. Notice because we highlighted this first key, right, this first cell, it labels it for us. In my specific data, it looks really nice because I made it up, right? So you notice they nearly overlap exactly as what we expect. And of course, you need to title your stuff. You need to put an axis title. I would actually even change where the label is, like the legend. I'd move it to the right side. Because if you put it on top, it looks like it's the title. So you need to also customize it and add the title and all that kind of stuff, right? We've done this before. Chart titles and axes. Name this maybe range versus angle of launch, right? Y versus X is always a good title. And then make sure you label your axes with its appropriate units and everything like that. Okay. Something you want to make sure of, all your values here need to be in meters. You shouldn't have anything still in centimeters. Okay, other than that, this is your data presentation. You need to explain your data or interpret your data by explaining if there's a large difference between your two graphs, you need to explain why that could be. Okay, what do you notice about your data that can explain why they don't completely match up? All right, so this is the video for lab number 5, the second experiment that you did, which was the general projectile.